Hi, AP Stats. This is Mrs. Hardy again. Today we're going to talk through lesson 7.3b on the central limit theorem. Just to kind of review what we talked about in class today for section 7.3. We calculated the mean and standard deviation of the sampling distribution of sample means and interpreted the standard deviation. Today we're going to continue talking about the shape of the sampling distribution of sample means, how it's affected by the population, how it's affected by the sample size, and then we're going to get into when you can apply a normal distribution to calculate probabilities involving the sampling distribution of sample means. So let's switch over. Here's activity 7.3b, which you should find in your OneNote. We have seen in the previous investigation that even though the distribution of the population of the ages of 1,000 pennies was skewed to the right, the distribution of sample means appeared to be approximately normal when the sample size was large. We don't have a cutoff number yet for what's large, but that's what we're going to look at today. We also know that if the original population distribution is normal, which is often the case, then the sampling distribution of the sample means is also approximately normal. So what that's saying is if you know that the population is normal, the sampling distribution will be normal regardless of the sample size. So knowing that the population is normal is enough justification for saying that the sampling distribution is normal. Today, what we're going to look at is when the population is not normal. So it says the question that arises is when can we assume that the sampling distributions of sample means is approximately normal if the population isn't? When we're talking about sample proportions, we talked about expected number of successes and expected number of failures being at least 10. This doesn't apply here. It's not the same scenario. So what we're going to take a look at today is figuring out what is this number? What is the large enough sample size to say that the sampling distribution is normal even if the population is not? So if you look at your screen, you have this distribution here. It is not normal. This distribution is called a beta distribution. So just take a minute and think about what you might say about the shape. It's clearly bimodal, it's somewhat symmetric, and those peaks, those modes, appear to be at the minimum and the maximum values in the population. So then what we're going to take a look at is this exact distribution in Fathom, and we're going to manipulate the sample size so that we can determine when the sampling distribution becomes normal. Okay, here is the Fathom file. Let me just kind of explain what you're looking at. Over here on the left is the population distribution that you just saw with a mean of 0.50, population standard deviation 0.35. This is the distribution of sample data. Right now, the sample data is set up to select sample sizes of 1. So the sample data is literally just one dot there. This over here is where we will collect the sampling distribution. So I can sample more cases and you'll see the sample distribution change. So if I sample another one case, you see it change there. Sample another one, you'll see it change there. Over here, I can collect many samples of size 1. If you look here, what we're going to be doing is we're going to be collecting 500 samples of size 1. So if I go through here and I collect more samples, you will see the sampling distribution change just a little bit. So here is one sample. Here's the sampling distribution of 500 samples of size 1. Now it should make sense that this is exactly the same as the population. A sample size of 1 is essentially just pulling items from the population. So this is what it looks like with a very small. As expected, the mean and the standard deviation are very similar to what the population mean and standard deviation are. So let's increase the sample size. I'll click here. What if we increased it to just 2? How does that change? Slide that down here. So now I can do sample more cases. Now you see 2 dots. That's another sample. Here's another sample. If I want to create this sampling distribution of sample sizes of 2, I will hit collect more measures. It's going to do 500 samples of size 2. And you can see already just changing it to a sample size of 2 has a pretty big impact on the shape of the sampling distribution. Okay, so how does the mean and standard deviation of the sampling distribution compare to the population distribution? The mean is still relatively close, 0.50. The standard deviation now is a little bit smaller. Let's go even bigger. Let's go 5. Sample more cases. Now you can see this one in the middle here is the distribution of sample data. There's 5 dots there. I could keep doing that over here. And here I'm going to collect more measures. And you'll see what the sampling distribution looks like. This is 500 samples of sample size 5. The mean, 0.5, 0.49. The standard deviation now is much, much smaller. We can go even larger. We can go sample size 10. So now the sample distribution has 10 dots on it. I can have the program generate 500 samples of size 10. And you can see in here, the mean 0.495, 0.50. The mean is staying pretty similar. The variation, on the other hand, is getting smaller. And you should notice that here in the image of the sampling distribution also, that the variability is going down. The shape is becoming more normal as the sample size gets larger. So even with a sample size of 10, take a look at the population distribution again and the sampling distribution. The sampling distribution is getting more normal. The mean is very close to the population mean, and the standard deviation is much smaller than the population standard deviation. I'm just going to go through and I'm going to continue increasing. 25 for the sample size. You can see the sample distribution, 25 dots. We'll go here and generate a partial sampling distribution of 500 samples of size 25. Takes just a second here. You can see it's gotten even tighter, less variability. The sampling distribution standard deviation is now 0.07, but the mean is still very similar to the population mean. I can go up to 50, and you can see population distribution, sample distribution, and I will go through and have the sampling distribution generated. The larger the sample size, the more time it takes here for Fathom to generate the sampling distribution. So we'll just wait a second. I think you can probably anticipate what's going to happen. The shape should continue to be approximately normal. The variability decreases even more, 0.05. The mean of the sampling distribution is still at the mean of the population. We could do 100. I think it would take just a few seconds there to generate the sampling distribution, and I think that you can already anticipate what's going to happen over here. So then here in your activity, we just did this part D right here. We increased it to 2, 5, 25, 50, and so on. What appears to be true about the shape, center, and spread of the sampling distribution, the shape becomes more normal. The mean stays pretty constant at the mean of the population, and the standard deviation decreases. So what you should have seen in there is that even though we have a population distribution that's extremely non-normal, the sampling distribution becomes approximately normal as the sample size increases. This idea is something called the central limit theorem. The central limit theorem is the basis for a lot that we do in third quarter, so it's important to understand what this is saying. It says if you draw an SRS of size n from any population, doesn't matter what the shape is, with a mean, mu, and standard deviation of sigma, the central limit theorem says that when the sample size n is large, the sampling distribution of sample means is approximately normal. And that's regardless of what the population looks like. If we know that the population is already normal, you don't have to invoke the central limit theorem to say that the sampling distribution is normal. You already have it. But if you have a population where you don't know the shape of it, or you do know the shape of it and it's not normal, then if you have a very large sampling size, you can still say the sampling distribution is normal. So what exactly is this sample size that would be large enough? Well, there's no set number that makes it okay. A general rule is to say that it's 30. And that's the number that we'll use throughout this class, is that if you have a sample size of at least 30, that is enough to say that the sampling distribution will be normal due to the central limit theorem. Now, there might be times when we are satisfied with a sample that is less than 30, but that's when the population is close to normal. And if you read here at the top, it says smaller sample sizes may not yield a normal sampling distribution. The central limit theorem may be safely applied if the sample size exceeds 30. If the population distribution is reasonably close to the normal distribution, then sample sizes of 15 to 20 are often large enough to say that the sampling distribution of sample means is approximately normal. You still need to ensure all of your other conditions to apply the central limit theorem, but you may see from time to time that we call it good enough for smaller sample sizes, and then that would be because the population is very closely normal to begin with. Let's just review here at the bottom the conditions that need to be met before you can use a normal distribution to approximate the sampling distribution of sample means. The first two you're familiar with, the randomization. The data must be from a simple random sample of the population. This creates an unbiased estimator. The independence condition. The sample values must be independent of each other. This one needs a couple of aspects analyzed. First, there's the 10% condition. When you're sampling without replacement, you want to make sure that you're not sampling more than 10% of the population. So you need to be sure that your sample size is less than 10%. And also, the fact that the data is taken from a simple random sample also contributes to independence. If those two things are taken care of, we can say the independence assumption is met. The large enough sample is the rule that we just came up with of 30 or more in the sample. Okay, let's pull all this together and look at how it might apply to an actual scenario. In question 2, it says male blue throatbirds have a complex song. Let X denote the duration of a randomly selected song in seconds. Suppose that the population mean of the song is known to be 13.8 and has a standard deviation of 11.8 seconds. The population distribution of X is also known to be non-normal. It's important to note. Suppose you select an SRS of 25 blue throat birds and measure their song durations. The first condition is random sampling from the population. Did we meet the condition, and why is this important? Well, we did meet it. It says it right there that it was a selection of an SRS. We want the sample to be a good representation of the population. We don't want to end up with a sample that's biased in any way. We want to get a good representation. So that condition has been met. The second condition is independence. Do we reasonably meet this condition? Yes, we've met this condition. 25 is likely less than 10% of all the blue throat birds, and the sample was randomly selected. So we can say that the independence condition has been met. So what about that last condition? The third condition is normality. Can you safely assume that the sampling distribution of sample means is approximately normal? Why or why not? What if the population was approximately normal? Well, in the beginning, the answer is no. The population is known to be not normal. That was given to you. And the sample size is less than 30, so the answer is no. What if the population was approximately normal? If the original population had been approximately normal, then it would have been fine to proceed regardless of what the sample size was. So in this case, 2 of the 3 conditions were met. All right, let's take a look at this. Question number 3. A hot dog manufacturer asserts that one of its brands of hot dogs has an average fat content of 18 grams per hot dog with a standard deviation of 1 gram. Consumers of this brand would probably not be disturbed if the mean fat content is less than 18 grams, but would certainly be unhappy if the mean fat content content exceeded 18 grams. Suppose we let X denote the fat content of a randomly selected hot dog and that we select an SRS of 36 hot dogs. Suppose that we find from our sample of 36 hot dogs that X bar, that's the mean, is 18.4. So we took a sample of size 36 and found the mean of that sample to be 18.4 grams. If the manufacturer's claim is correct that the mean fat content is 18 grams, then what's the probability that from our sample we would get a mean fat content of 18.4 grams or greater? In other words, we're looking for the probability that X bar is greater than or equal to 18.4. Let's go through and check the conditions to see if we can apply a normal approximation to this sampling distribution to determine where our sample of 36 hot dogs would fall on that sampling distribution. Here are the 3 conditions that we need to discuss. First of all, was it randomly selected? It did say an SRS was taken, so we can assume the sample is a good representation of the population. The randomization condition has been met. The second one is independence. 36 is definitely less than 10% of all hot dogs, and it also said that it was a simple random sample, so we can assume independence. And then the normality condition. The shape of the population distribution is not even commented in there. It could be normal, it could be non-normal, it could be very non-normal. But because the sample size is over 30, the sampling distribution can be assumed to be approximately normal. So with all of these conditions met, we can find the mean and standard deviation of the sampling distribution, and we can apply a normal approximation to determine what's the probability of getting a sample of size 36 that has a mean 18.4. So we're going to apply the formulas from yesterday. The mean of the population is 18. That's the claim, right? The mean, that mu is 18. The standard deviation then is 1/6. You had a standard deviation of 1 over root 36, root n. So basically, we're finding the probability that X bar would be greater than or equal to 18.4. We're getting a z-score for 18.4, either using the table or your calculator. We come up with 0.0082, a probability of 0.0082. So based on these results, do you think the manufacturer's claim is correct? Explain your reasoning. All right, so let's think about what this means in context. This means we have a 0.82% chance of getting a sample with a fat content of 18.4 or greater in a sample size of 36. So, do you think the manufacturer's claim is correct? Based on the results from Part A, we're going to say no. Assuming the mean is 18 and the standard deviation is 1, there is less than a 1% chance that we would get a sample mean of 18.4. This leads us to believe that the actual average is greater than 18. So they're claiming that it's 18, but we came up with this sample that is actually quite rare. Less than 1% chance of getting a sample with an average of 18.4, but we did get it. Now remember, it doesn't mean that it's impossible. It just means that it's unlikely. It's unlikely that we just randomly got this rare sample with a mean of 18.4. But the fact that we did get it means that maybe our original assumption that the sampling distribution was based on, maybe this original assumption is wrong. We have evidence to suggest that it's actually greater than 18. So just like we had a diagram with the rule for sample proportions, you can take a look at the diagram here, applying the central limit theorem. The sampling distribution is approximately normal if the sample size exceeds 30 or if the population distribution is already normal, with a mean at the population mean and a standard deviation here. So scroll ahead to the last question to check your understanding. Get down here before you can see the answer. Says everyone wants to have the latest technological gadgets. That's why iPods, digital cameras, smartphones, Game Boys, and the Wii have sold millions of units. These devices require lots of power and can drain batteries quickly. Battery manufacturers are constantly searching for ways to build longer lasting batteries. A particular manufacturer produces AA batteries that are designed to last an average of 17 hours with a standard deviation of 0.8 hours. Quality control inspectors select a random sample of 30 batteries during each hour of production, and they drain them under conditions that mimic normal use. Below is one sample. The average lifetime in the batteries of this sample is 16.7 hours. Do these data suggest that the production process is working properly? Are plant managers safe sending out all the batteries produced in this hour for sale, knowing the claim on the outside of the packaging? Use what you've learned in the chapter to answer these questions. So I'm going to give you a couple of minutes to go through and apply what we just talked about to determine whether this claim can be believed or if there's evidence against this claim. All right, so before you start any problem involving a sampling distribution, you need to go through and make sure that conditions are met before you proceed. So first of all, it needs to be a random selection process. And it does say an SRS was taken, therefore we can assume the sample is a good representation of the population. The second condition is independence. Remember, there's two things that contribute to that. The first is the SRS, which we already established happened. And then 30 is definitely less than 10% of the population. It's likely that any company out there produces more than 300 batteries of any given type. And then the normality condition, condition number 3. The shape of the population distribution is unknown. We don't know what that looks like. But because the sample size is 30, we're going to proceed assuming that the sampling distribution is approximately normal. So with the conditions met, we can find the mean and standard deviation of the sampling distribution. The mean is the mean of the population, 17. And here's the calculation for the standard deviation of the sampling distribution. So then we would like to figure out what's the probability of getting a sample mean of 16.7 or less. And some of you might be wondering about that or less. And think about when a company makes a claim about a battery life. Is anybody going to be upset if the battery actually lasts longer than what their claim is? Probably not. So the thing that we're trying to figure out is, does it actually have a lower battery life than what's advertised? And we got an average of 16.7, so we're concerned with 16.7 or less. Get your z-score for 16.7. Find the probability that z is less than or equal to negative 2.06. You get 0.0196. And we talked about anything less than 5% is considered to be unlikely to have happened by chance. It's not that it couldn't, it's just that it's unlikely. So in our conclusion here, if the mean is truly 17 and the standard deviation is 0.8, then there is less than a 2% chance of getting a sample mean of 16.7 or less. Therefore, that leads us to believe that the true population mean is less than 17 and the process is not working correctly. Our calculations are based on the assumption that the true mean is 17, but we came up with a sample that was quite rare, which leads us to believe that our original assumption is actually incorrect and that the true population mean is less than 17. That brings us to the end of 7.3b. If you have any questions, please let me or Mr. Bowman know.